Hello everyone. In this video, we'll be looking at software clock experiment, which has three components working together: the 8085 microprocessor and LCD display module and a programmable peripheral interface chip, which is 8255. In this experiment, we haven't used any kind of timer or counter or a software clock directly. Instead, we have used the LCD display and the internal timing mechanism of the 8085 microprocessor to create a software clock. Now let's look at the objectives of the experiment. The primary goal is, of course, to demonstrate how a LCD display can be configured using the input-output lines of a programmable peripheral interface. However, we have also done, that is the main goal of the experiment. We have also created a software clock which shows hours, minutes and seconds only using the instruction timing of 8085. That is, by counting how many T states are required for 1 real second, we have configured it to create a clock. We will look at what a T state means in further slides. The second objective is to display the timing on the LCD screen. For this, we just have to connect the display to the 8255 programmable peripheral interface chip, and it must update every single second. The program we wrote achieves this through subroutine calls, and I would also explain what subroutine means in further slides. The display is refreshed every single second to show the updated time. The third and the most important objective, according to me, is the measuring the crystal frequency. So comparing this clock against some kind of stopwatch from our mobile, we can see how much offset is present between the software's clock and our mobile's stopwatch, because our mobile stopwatch will be very accurate compared to 8085's timing circuit, and this can be used to find out defects in the crystal frequency or the timing of the microprocessor. So now let's look at the apparatus and the devices used in the experiment. The first is 8085 microprocessor training kit, which was made by Excel Technologies, and we also need a flat ribbon cable, and of course we need the LCD module CTS 1612, which was also made by Excel Technologies, and we also need other trivial devices such as connecting wires, and of course we need a power supply. All of these images were taken in the microprocess lab in the physics department of IIT Roorkee. Now let's look at the pin diagram and the working of the LCD module. First of all, an LCD means a liquid crystal display. So there is a significant difference between LED and LCD displays. LCDs use liquid crystals to selectively block or allow ambient light to pass through. This can be explained by the polarization of light, but we'll not get into the physics of it in this video. They consume very little current, and they are ideal for battery operated embedded systems. Also, the CTS 1612 is a character LCD, which means it can only display a certain amount of characters and a certain shapes, which can be specified through their ASCII codes. Unlike something known as a graphical LCD, where we can display any kind of animation, that is not possible in this LCD module. The matrix consists of 5 cross 7 dots per character. Each character cell consists of a grid of 5 columns and 7 rows of tiny liquid crystal dots. The controller uses this dot matrix to draw the shape of each character. For example, to show the color A, we light a specific amount of matrices, maybe something like this, and then we have to light this up, then light this up. Something like this can be done. Similarly, we can also show other characteristics using this. So there are 14 pins, which is shown in this diagram. We can see the power pins, control pins, and the data pins. The 14 functional pins, and then the 2 pins are actually for backlight versions. The 3 pins handle the ground, power pins, and supply and the contrast. The control pins tell us what kind of data is arriving to the LCD and when to read it. For example, the read or write tells the LCD whether to read or write it. And the enable pin, when it gets high to low, that's when the LCD actually performs its action. The 8 data pins actually carry the command or the character byte. For example, if we give it an ASCII code, it has to understand what it is. So the data pins actually transfer the codes to the LCD module. So now let's look at the pinout diagram classification of the LCD module. VSS is the ground for the LCD. It must be connected to the common ground. And this is the power supply. And this is for contrast adjustment. This controls the display contrast, how dark the characters appear against the background. It is connected to the end of a potentiometer, which we can modify and then control the contrast. This RS means register select. This is a critical control pin because when RS is equal to 0, the LCD interprets the bytes on the data pins as an instruction or a command, like turn the display on, or clear the screen, or set cursor position. The cursor position is where the LCD starts to display characters. However, when RS is equal to 1, as you can guess, it interprets the bytes on the data pins as a character data to be displayed. For example, if it tells 1000, then it reads this as an ASCII code and then displays the specific character corresponding to this ASCII code on the LCD screen. E is the enable signal. The LCD actually only reads when or processes what's on the data lines only when the enable pin transitions from high to low. We will look this in detail in the next slides. And these are the data pins. I've already explained what these mean. They are connected to the port A of the 8255, and this diagram shows us all the pins of the LCD connector. This is VSS, VDD, and these last two pins are for backlight LED anodes. Now let's look at the pinout and signal classification, and in this section I'll be explaining what the RS and R/W pins mean. The register select pin actually tells the LCD whether or not to recognize something as an instruction or as a character to be displayed. When RS is equal to 0, the LCD is in instruction mode. The byte on the data bus is treated as a configuration command. Examples of command include, for example, clearing a display, which is given by 01H, setting the cursor position, which is given by 80H to CFH, where each of the hexadecimal digits from 80H and CFH actually refer to the different blocks in the LCD matrix, since we have two rows and 16 columns. These commands change the internal state and configuration of the LCD controller, but they do not really put any kind of visible character on the screen. And when RS is equal to 1, it means that LCD is in data mode. The byte on the data bus is read as the ASCII code of a character to be written in the display data RAM at the current cursor position, and that character then becomes visible on the screen. For example, if I give 0x41, which is the ASCII code for A, then the LCD will display the letter A. This has to be converted into hexadecimal, of course. Then this character A will be displayed on the cursor wherever the cursor points to. After that, the cursor automatically advances to the next position. This is almost like a stack pointer in a 8085 microprocessor. And this distinction is the most fundamental concept in programming this LCD. Every interaction with the LCD is either a command or data that is to be displayed. So now let us look at what the R read and write pin means. When this pin is equal to 0, it means the microprocessor is sending data to the LCD through an operation. It is basically a write operation. This is both used for writing commands and writing the display data. When this pin is equal to 1, this means the microprocessor is reading data from the LCD. The most common read operation is checking the busy flag of the data bus. However, in our experiment, we are not using that mode of the LCD, so we don't have to bother ourselves much with it. Now let's look at what the enable signal means. The enable pin is actually one of the most important pins in any kind of circuit or software. In the LCD display, the LCD actually looks at the data pins only when the enable pin falls from high to low. So that's what I've written here. For example, in any kind of sequence, we put the correct data on the data pins, then we set RS and RW, then we raise E high. The LCD now sees the data but hasn't acted yet. After a short setup time, that is this time TDSW, we have something known as a falling edge in which the enable pin goes down to 0. Only at this falling edge, the LCD would read whatever data is being sent to it. The enable cycle time is usually more than 500 nanoseconds. The total time from one enable high to low pulse must be at least 500 nanoseconds. And this is why delay routines are called after every command or data write. The 8085 runs almost on a 3 megahertz crystal, and which is about 320 nanoseconds each. So a few instructions can easily provide this kind of delay which is required before that enable pin actually can be read by the LCD display. So we will look at how this enable signal and the timing delay is used in the code analysis part of the slide. So now let's look at the memory and the addressing. The first question which most of you would have is how the LCD actually displays the data. The internal memory of the LCD is something known as a DDRAM. Each address in the DDRAM corresponds to one character position on the screen. For example, we have 16 rows and 2 rows and then 16 columns. So each of the 32 positions is given by some kind of address in the DDRAM. The DDRAM can hold up to 80 bytes, although only 32 positions are visible at once. The LCD maintains an internal pointer called the cursor, which always points to a specific DDRAM address, and whatever data you give to the LCD will only start from the cursor. When we send a byte with RS equals 1, the LCD writes that byte into the DDRAM at the current cursor address and displays the character, and then automatically increments, as I explained earlier. This auto increment feature means, of course, that we can write a sequence of character one after another without manually repositioning the cursor each time, which is very convenient. To set the cursor position, we must first send a command to the DDRAM address. For example, to set the cursor to line 1 position 6, line 1 position 6, we have to send the command 85H to the DDRAM with RS equals 0, because 80H is the base address of the line 1, and adding 5 would give us the 6th position. After that, we can send the character data with RS equals 1, because as I explained earlier, RS is to differentiate command mode and then character mode. So now let's go to the address map of the DDRAM. So this is just the address map. This is first line and this is the second line. This is for each column. So this starts with 80 and then ends in 8F. And the next line starts in C0 and ends in CF. So you can see that a lot of addresses in the middle are skipped, like 90H and then A and then B. So the actual reason is because they are hidden from the actual memory and they are stored as a buffer memory. If we keep writing characters without repositioning the cursor, the characters beyond position 6 do not go into this hidden area unless you use the display shift command, which we will be looking later. It is actually a design artifact of the architecture. It means that to write on line 2, we must explicitly send a command to jump the cursor to C0H. So now let's look at the address range of the DDRAM. So as I said, these are the ones which were missing in the last slide in the address map. Now let's look at the reason for why we have them. These are 16 visible character positions of line 1. Writing ASCII characters to these addresses actually displays them directly in the first row. And these 24 bytes, both of them, are actually in the DDRAM space, but they are not displayed because they serve as a hidden buffer that allows the line 1 display to be scrolled horizontally using the display shift command. For example, if we have a text longer than 16 characters, we can scroll them across the first line, right? Otherwise, we would not be able to see, for example, if your name has more than 16 characters, and since we have only 16 columns, we might not be able to fully display your name using this LCD display. But still, we can scroll the whole text. You could have seen this in televisions and news channels. The text actually scrolls, and then we will be able to see the entire text. So you can use this buffer memory to scroll the text. Although this is not the mechanism used in televisions nowadays, of course, but you can think of it as an analogy. And this is just the same as this. There is nothing new in this C0 to CFH. So now let's see an example program in which we can print some text, let's say Excel, at the first row, starting from a specific cursor position. So the line 1 starts at the DDRAM address 80H, as we saw in the previous slide. And we need to skip the first 5 columns because we have set the cursor position to column 6. That's just arbitrary. We could have set it to anything. We have selected 6 because it's roughly in the middle. So the target address is 85H. And then the first line of the code, we have to, this is a 2-byte instruction. The opcode 3E means move immediate to accumulator. And this is the operand value, which is the DDRAM address for command for line 1 and column 6. So this is just setting a DDRAM address. This is just setting roughly you can think of it as setting the cursor position. And this calls a subroutine, which is present not here, but that's a specific code which we'll be seeing in further slides. So yes, after this call, the LCD's cursor is positioned. Then to actually print Excel, we have to send the ASCII code for each by using the WR-char subroutine with RS equals 1. So at this position, we have to, we will look at what the WR-CHAR subroutine means in further slides. So let me first erase these. So now let's look at what the entry, mode set, and port mapping mean. We can use the control signal mapping through the 8255 and the entry mode set command. This table shows how the LCD control signals are mapped to 8255 ports. For example, this register select is connected to PC0, that is port C bit 0 of the 8255. When the program outputs a byte to port C with bit 0 set to 0 and RS equal to 0, which is the command mode, and read or write is connected to port C bit 1 of the 8255. We always use read or write is equal to 0 because we are not reading anything from the LCD as I explained earlier. And enable is connected to port C and bit 2 of 8255. To pulse enable, the program must first output a byte with bit 2 equals 1, which is E high, and then output a byte with bit 2 equals 0, which is E low, enable as low. The data bus comes from port A. The full 8-bit command or character byte is output to port A before pulsing enable. So now the entry mode set command. After every DDRAM read or write, the cursor direction moves right or left. IND equals 1 means the cursor increments, which is the normal behavior for left to right text. When the entire display is shifted when new characters are written, we can set S equals 0 for not shifting anything and the display to make the display stay fixed and to only move the cursor. So now let's look at the instruction set of the LCD. So 38H is a hex code. This command configures the, let me select this. This command configures the LCD hardware. When DL equals 1, it means the 8-bit data bus means 8-bit data bus are all used simultaneously. N equals 1 means 2-line display, and F equals 0 means the 5x7 dot matrix font, which I explained earlier in the first 3 slides. This must be sent at least 3 times during power on initialization as per our LCD controller to set the interface mode. Then we have 0CH, which turns on or turns off the display. This means the display is turned on. C equals 0 means the display is turned on, and B equals 0 means the blinking clock cursor is not shown. This is to set the entry mode, which I explained in the previous slide. And this is to set the DDRAM address. We just saw this in the last 3 slides. And this is the same. This is just setting the DDRAM addresses. These are just different addresses. So now let's look at the circuit diagram. So this is the most important slide for understanding the hardware, I would say. This VCC and ground, they are actually just for power supply. And X1 and X2 are the, let me select this. So if we zoom in here, this X1 and X2, they are the crystal oscillator pins, and this determines the frequency of the clock. You can see this here. And this reset signal is connected to the reset pin of the 8255 to reset both chips simultaneously. And this is the address latch enable. These are specifics of the 8085 architecture, which we are not really going to discuss much here. And these are read and write pins. These are used by 8085 to control data transfers. And this signal distinguishes between memory access. It is connected to 8255's chip select logic so that the 8255 responds only to input-output instructions. This is the address or the data bus and pins, and this is just the address pins, upper address pins. And this is the clock, of course. And this is the address latch, which is 74LS373. This is a transparent latch. It captures the lower address bits from the 8085 when ALE is high and holds them stable for the rest of the machine cycle when ALE goes low. It outputs Q0 to Q7, as you can see here, and then which is the demultiplexed lower address bits. So now the next block is the 8255 programmable peripheral interface. These are the data pins. These are the same pins as I explained earlier, VCC and ground. This is the reset pin. This is the read and write pin. This is the chip select pin. The address decoding logic actually generates the chip select signal to select only the 8255, select the 8255 only when the 8085 is performing an input-output operation at the correct port address. And these are the different ports in 8085. Now this is the CTS 1612. All these pins we have already seen their functions earlier. Now let's look at the connections here. So RS is connected to port 0, PC0 of 8255, and the data pins are connected to PA to P7 of 8255. And these are the backlight pins, which are connected to a potentiometer, as I explained. And this is just a legend, and yeah, this we've already seen. So now let's look at the program logic flowchart. The first part is initializing the 8255 PPI. So the very first thing the program does is configure the 8255 by writing the value of 80H to its control word register. The address of control word register is 03H because A1 equals 1 and A0 equals 1 selects the CWR, and 110 means 03H in hexadecimal. 80H in binary is, it would take maybe a few seconds of calculation. You can figure out it would be something like 100 and 0000. The MSB being 1 in this means that this is a mode set operation, and this is not a bit set. reset operation. This is not a bit set reset operation. And then the remaining bits encode mode 0 for all ports, and then all the ports as output ports, which is necessary because we are only writing to the LCD and we are not reading anything from the LCD. So because of that, we don't need any kind of input modes. After that, the LCD sends commands using the send command subroutine, and then it sets the cursor at the required position, and then it prints the character XL, and then it sets the cursor to the second line. And now we have to again change the DDRAM address because we want it to be in the second line and position 5, because XL and welcome are on different lines. Then to print welcome, we write character by character, WELCOME. This is just to write a sample program and to write XL welcome. So this is not what we are actually doing in this experiment, which is about a software clock. This is just to explain the basics of LCD matrix. Now let's look at the code of our actual experiment. So you can start here. So you can see this. So 3E80 corresponds to the mnemonic MVI A80H. This is to load the control word 80H into the register A, which is the accumulator. We are sending this to the accumulator. You may ask why we do this. Actually, we do this in every experiment because this is to give the control word to the 8255 PPI. Then in here we specify the output ports, and this is the port address. As you can see, 03H is the port address. This sends the value in the register A, which is 80H, to the port, and the 8255 interprets the value written as a mode set command, as we saw earlier. So now let's look at the next parts of the sections of the code. 38H means 0011 0000 in hexadecimal. So this is sent 3 times because the controller in the datasheet of the controller actually specifies that on the power up, the initialization sequence requires the function set command to be issued multiple times with a specific timing. And sending this command only once may leave the LCD in an uncertain state. So that's why we send it 3 times actually. That's it. So now you can see this command here, 0CH. 0CH actually means 0 0 0 0 and then 1 1. As I explained earlier, this is to the display. This is to set the display to active, but the characters, and to ensure that only the characters we write will appear. So then you can see 06H. This might be familiar to you. This is only to set the cursor to the 6th position of the first line. Rather than that, we can say this is to increment the cursor by 1 whenever we write something. Then you can see this. This is the clear display command. It fills all the DDRAM addresses with the ASCII space and then resets the cursor back to address 80H and resets the entry mode shift. And this is particularly slow actually. This takes about the slide has changed. Wait a second. Yes, it takes about 1.64 milliseconds. You can see that here. Let me just erase this. So let's move on to the next section of the code now. So this is the main clock loop actually. As you can see, this is a 1-bit instruction. Instead of doing XOR, we can also do MVI A00H, but that's a 2-byte instruction, and this is only to optimize the timing. This takes lesser number of T steps as compared to that. And then this is to store the accumulator contents in the specific RAM locations, and this stores the hours, minutes, and seconds. And then you can see in this we activate the subroutines show time delay for 1 second. And then you can see the other commands here. These are just different subroutines to fulfill the necessity of our program. We'll look at each of these subroutines now one by one. So, and this is the subroutine write command to the LCD. So basically what this does is the command byte that was placed in register A before calling this command is output to port A. This puts the 8-bit command line on the LCD's data lines. Then we have MVI A04H. This is loading 04H into the accumulator. 04H is nothing but 0 0 0 0 0 1 0 0. In this bit 2 is equal to 1 and bit 0 equals 0. So RS equals 0 and read or write pin equals 0 and enable equals 1. And there is out 02H, output to this port C. This is output to port C. This raises the enable pin while keeping RS equals 0 and read or write equals 0. The LCD sees the command byte on the data lines with RS equals 0. And then we have MVI A00H. All bits 0 means enable equals 0 and RS equals 0. This means the enable goes to low, and this high to low transition, as we saw earlier, causes the E pin, causes the LCD to latch the command byte from data lines, and it starts executing it. Then it returns to the calling code. And this is the section for write character. And this is just the same. To be honest, this is not much different. I mean, the mnemonics we used are almost the same, and you can read them and then understand them by yourself. But still, what this does is RS equals 1 puts the LCD in data mode, so when E falls, the byte on data is written as an ASCII character. The only difference between the last slide and this is that in this slide, in this section of the code, it's treated as a character. In the last section of the code, it was treated as an instruction. So now let's see, these are the delay subroutines. So in this, 64 is loaded into register C, and then the register is decremented by 1. This takes 4 T states, and then we have a conditional jump, which goes back to the DCRC instruction. When the condition is true, this takes 10 T states, and when C equals 0, it falls through and takes 7 T states. So each loop takes about 14 T states. So at 3.072 megahertz, each T state takes about 320 nanoseconds. So the delay here is about 291 microseconds. This is sufficient for the enable cycle time requirement for normal data writes. And this is delay 2, which is a longer delay. The only difference is here we are using FFH instead of 40H, due to which this is a longer delay. So next is the delay for 1 second. In this, again, this is not much different from the last slide either, although this is a much longer delay. So this is a nested double loop delay. You can see the inner loop has addresses from 2077H to 207AH. The 8085 doesn't have one single instruction to check if a register pair is 0. So we use a trick, that is we use a command which is move AB to move the copies to upper byte of BC into A, and then we use OR A, which is a bitwise OR operation, to use OR between C and A with the lower byte as C. If both B and C are 0, then A or C will be 0, then which would set the 0 flag. And J and Z, which is jump not 0, does not jump. Otherwise the loop keeps continuing. So here we have 63,999 iterations, as you can see here, and this multiplied by 24 T states would give us 1.5 times 10 power plus 6 T states per inner loop run. And since we are setting D equals 2 here, this would make it twice, which is nothing but 3.072 into 10 power 6 T states, which is nothing but 3.072 megahertz. Since this has exactly the same amount of T states as the frequency of the crystal, this means our delay is totally of 1 second. And this is what sets the basis for the clock. So this is the code for the software clock. This is to increment the time. This part of the code, although is necessary, is not really much different from the earlier sections of the code. The only new parts are the CPI, which is compare immediate, CPI. And the purpose of this section of the code is when we hit 60 seconds, we have to go back to 0. Similarly, for 60 minutes, we have to go back to 0. And for 24 hours, when we hit 24 hours, we need to go back to 0. That is what this section of the code does. You can see it. We have just used the same principles. We used XOR, and then we stored the accumulator value in the RAM, and then we loaded the RAM with the accumulator value, and then, as you can see, we used compare immediate. And this section of the code is to show the time. So in this, we just send the necessary bytes to the LCD in order to display what time is currently should be currently displayed. This is what we discussed already in the last program, which is showing Excel welcome on 2 lines. This is almost the same as that. And these are just the subroutines, display byte and write character and display byte. We already have seen them already. So this is the important part of the code. This is measuring our crystal frequency. So in our crystal, actually what happened was we lost 3.24 seconds over 900 seconds. I will show you that in the next video. So this means our crystal is 3600 parts per million slow, but that's not true because any crystal wouldn't have so much deviation. The reason behind that is, although we have used a 1 second delay, our entire code would take more T states, which would cause even higher delay. So after taking all of that into account, I figured out that the crystal frequency is actually 3.073 megahertz, which is a little higher than the frequency mentioned in the datasheet. But this is actually not well within the range, but still this is normal for a training kit microprocessor. In fact, having this crystal frequency to be higher caused our program to have a better result. So this is the video for the first program, which is just Excel welcome. So you can see it here. After we run the command G2000, the text Excel welcome appears on the LCD display screen. You can see it very well here. This is just a simple program. Now we'll look at our actual innovation or the experiment, which is software clock. So you can see here, after writing the command G 2000, so the timer has started here. Although I call it a software clock, to make this into an actual clock I just have to set the time once in this, and then it will start behaving like an actual clock. It would be more appropriate to call this a stopwatch, but it's not very different when we are talking conceptually. So I don't think any of us wants to see the stopwatch just running for on and on for a lot of minutes. So something interesting that we can do is place a actual stopwatch against this and then calculate how much delay the LCD, or how fast or how slow the LCD is compared to the actual stopwatch. So that's what I exactly did in the next video, although I did not click up video of all the entire 15 minutes. I just clicked it when it reached its 15-minute mark. You can see. So the LCD is working fine as a clock. However, there is an offset by 2 or 3 seconds, as you can see. So when we pause it exactly at this moment, it's at 57, and this has crossed 15 minutes exactly almost. So this means we have a delay of around 3 seconds for every 15 minutes roughly, and with this information we actually calculated the actual clock frequency of the crystal in the last 2 slides. So that's it, we're done with our video. We'll just now briefly look at the conclusions. So our goals were to achieve a software clock, and we succeeded in that. We built a software clock purely displayed on the LCD, driven by the 8085 microprocessor instruction timing without any external hardware. The entire program architecture has subroutines for initialization, delay, display, and the conversion. This is the same architecture used in professional settings, and we also measured the crystal frequency roughly. To detect any kind of faults in the crystal or inside the microprocessor circuit, this experiment can be widely used. Although any big defect or any big deviation from the actual crystal frequency will be apparent in any kind of experiment, this experiment can be used to find out small differences in the crystal's oscillating frequency. So that's it. Thank you for watching the video. These are the references for some of the images used in the presentation, and all the other images and videos were taken in the Microprocessor lab of physics department in IIT Roorkee. Thank you.